everyone. Welcome back to the interactive stargazing with Lowell Observatory. For those of you who this is your first time watching, welcome. My name is Hannah Zigo. I am an educator and research assistant at Lowell Observatory. And tonight we're going to be looking at a whole bunch of different cool objects up in the sky. The moon is currently rising, so we're going to try to look at some deep space objects first, and then try to get some of the brighter ones like the planets a little bit towards the end, but they are setting. So we're going to get to those pretty soon. So we already have our first object up right now, which is the NGC 891 galaxy. And so I think this is a super, super cool galaxy because it's a completely edge-on galaxy from our field of view. And so we can see a lot of different definition in this galaxy compared to other ones. And so what we can see already on our screen is we can see a very, very thin, dark line, which is the disk of the galaxy. That is where the spiral arms are. And that's where all that star formation is happening. That's where all the exoplanets are, all the stars dying, all this active area in the galaxy is mainly in that disk, in that black line there. And then towards the center of the galaxy, that's the brighter region, that is actually the core or the central bulge of this spiral galaxy. So that's where a lot of the older stars are, but there's a lot of them. They're really bright. And so it makes it look like that the core of the galaxy is the brightest, but in retrospect, the disk of the galaxy is the most luminous compared to the core of the galaxy. And so I like this view of NGC 891 because it gives me a good kind of point to talk about globular clusters. And so we're going to look at globular clusters in just a little bit right after these galaxies. But when we do look at these objects called globular clusters, they orbit around the core of the galaxy. So they orbit around the galaxy's halo, which is this large scale feature. It surrounds the whole entire galaxy. But that's where these objects will be orbiting the plane of the galaxy. So just keep that in mind for when we do look at those coming up here in a little bit. And so a little bit more about this galaxy. It's about 27.4 million light years away. So it's pretty far. It's actually one of the closer galaxies to us. It's part of our local supercluster of galaxies. So things like Andromeda, Triangulum, Sculptor, things like that, galaxies like that, those are in our local supercluster. They're a lot closer to us than some of the other galaxies that we see. And the radius of this galaxy is around 60,000 light years, so it's pretty big as well. And then the age of this galaxy, they assume that it's around 13.29 billion years old. So it's a very, very old galaxy, has a lot of older stars in there. So again, it's a very awesome galaxy. I love that edge-on view. We can really see the central bulge of the galaxy, how it kind of extends out from the disk, which I think is awesome. But to compare NGC 891 to some of the other ones, let's go to the Triangulum Galaxy, just so we can still see a little bit of the different structure of spiral galaxies. So we like to look at spiral galaxies mainly here because they're a lot more visually appealing than some of the other galaxies. So we have a wide variety of galaxies up in the sky right now. We have elliptical galaxies, we have dwarf galaxies, we have starburst galaxies. There's all these different types of galaxies, but the ones that we can best see right now are spiral galaxies. And again, they're much more visually appealing. Elliptical galaxies are very old galaxies as well, but they're kind of just like this blob shape. So they really don't look good through the camera compared to these spiral galaxies. And so we have our image of the Triangulum Galaxy coming up right now. You can already see some of the structure of these spiral arms. I think this is a very, very beautiful picture. And right at the top right corner, kind of to the middle, you can actually see, I think that's a companion galaxy to Triangulum, which is super cool. But again, we can see some of the structure of the spiral arm. So you can actually see the shape of it. You can see some arms going all around it. And then you can see that core of the galaxy. And again, the core looks the brightest to us, but the disk is actually the most luminous. And so, yeah, it looks like the moon is rising a little bit. So we're getting a little bit of interference from the moon, but shouldn't be too bad. And Triangulum is a little higher in the sky. So it should be fine. But again, yeah, it's a very beautiful spiral galaxy. Really like the structure of that. It's one of the better ones in the sky, in my opinion. It's very large. And again, this one's a lot closer. It's around 2.7 million light years away from us. And it's a little bit smaller than NGC 891. It's around 30,000 light years across, or the radius at least. So it is a little bit smaller. But again, this is super, super cool galaxy. And so while we're looking at different objects, if you guys want to leave any recommendations of objects you guys want to see tonight and leave them in the comments, that would be super, super awesome. And we can look at some things that you guys have never seen before. But for now, let's go to a globular cluster. Let's try like M15. See how that is in the sky. I was just talking about globular clusters earlier and how they kind of orbit around the galaxy. So I think this is a good transition point. And so these globular clusters, again, are very, very old features. There's a lot of research still going into these features on their origin story. But M15 itself is around 12 billion years old. And so I was just telling you guys how those other galaxies were around 13 billion years old. And this cluster is 12 billion years old. So these clusters are almost as old as our galaxy. And so that kind of leads us to think that these globular clusters actually weren't formed in our own galaxy. We actually think that they were their own galaxy that was being formed, and during its formation, either the Milky Way or some other galaxy passed by and took them into their orbit, and then they started orbiting around the halo. And so there is the theory that these globular clusters aren't from our own galaxy, and they were their own little galaxies that we ate up. And so something else that kind of supports this theory is that a lot of these globular clusters actually have black holes in the center of them. And so these stars are very, very old, and they have a central black hole. So it's just more reason for us to believe that they were their own little galaxies. And so something else that's really interesting about these objects is, I said they're really, really old. So how do they still have these stars? Well, these stars that are in these globular clusters are also very, very old. They have had a lot of time to interact with one another. And I believe they are low metallicity stars, and so they actually live a lot longer than regular stars. So they're their own type of stars. They're very, very interesting. There's still a lot of active research going into these stars. And so I love globular clusters. I think they look super cool. All these stars just super compact into one tiny area. I believe they think M15 has around 500,000 stars, so 500,000 stars in it, which is incredible. And this globular cluster is in the constellation Pegasus. It's actually a little bit easier globular cluster to find. So if you guys were trying to find this tonight with a telescope or some binoculars, you should be able to find this one pretty easily. So yeah, that's a super cool object there. So now let's transition from globular clusters to another cluster, another type of cluster of stars, but it's a little bit different. So let's go to an open cluster. Maybe let's try, is the Pleiades up right now? I think the Pleiades are rising. I don't know if they're high enough yet. Or no, instead let's try the Owl. That one's gonna be, yeah, a lot easier to see. I believe it's like NGC 284 or something like that. But yeah, so either open cluster would be fine. Oh, I was completely off. 457. So now we're transitioning from globular clusters to open star clusters. So we have two main types of clusters of stars in the sky tonight, which is globular and open. So we just talked about globular clusters, and so these open clusters are actually a lot different than the globular clusters. They actually orbit inside our own galaxy, inside the disk of our galaxy, and they're actually very young stars. And so again, with M15, those stars were around 12 billion years old. These stars are fairly young. I believe the stars are around 21 million years old. So a lot younger. And so how these stars form in the open cluster is there is this big cloud of gas, and we call these nebulas. These big clouds of gas sometimes are so thick and they're so dense that they actually collapse upon themselves to make little baby stars. And so coming up here in about a month, we have a really, really great nebula, and it's called the Orion Nebula. And we call some of these nebulas stellar nurseries because they make baby stars. And so in about maybe like around a month or so, we should be able to see one of the stellar nurseries, the Orion Nebula. So unfortunately, tonight we don't have any really good stellar nurseries up to kind of show you this. But again, the Owl cluster is a really good example of what it looks like when these stars get older and they eat up all that gas. So when these stars are formed in this cloud of gas, they start to eat up all that material around them. And eventually all these other stars are being born. They're all eating up all this gas, and then all the gas disappears, and then we're left with this open cluster. And then eventually these stars will interact with one another and they'll move apart, and they'll just become normal stars, which is super cool. So again, it's kind of like the life cycle of stars. How we get these nebulas is from stars dying, from stars exploding. We get this gas that gets put out into space, and then all that stuff kind of coalesces and creates more stars. So we kind of got this cycle going on here. So to kind of demonstrate that recycling effect, maybe let's look at a dying star. So let's look at the Dumbbell Nebula. And so the Dumbbell Nebula, which we'll be moving to, is, again, it's a nebula. And so nebula is a word for like clouds of gas and dust in space. And then we have different types of nebulas. Like I was saying, we have stellar nurseries. And then this one is from a dead star. So this is actually a planetary nebula. And so it's kind of a misnomer. It actually doesn't have anything to do with planets. It's just kind of round like a planet. So that's why they call them planetary nebulas. But so again, this is a dead star and the remnant of a dead star, to be exact. So the Dumbbell Nebula, there was a star that was a little bit smaller than 3 solar masses. So we use the sun as a reference point to kind of measure the weight of different stars. So we say, okay, our sun is 1 solar mass. So if we compared it to other stars, what would their mass be? And so to create these planetary nebulas, they have to at least be under 3 solar masses, preferably under 1 solar mass is how these ones form. And so these smaller stars, these really, really small stars, when they die, the outer layers of the star kind of start getting pushed off into different shells. And then eventually all the gas from the outer shells of the star will be pushed off, and the core of the star will shrink down to something called a white dwarf. And so all those pretty colors that you're seeing there are actually the outer shells of the dead star. So you got some nice blue colors, we have some red, and that is the different elements that were actually in the outer shell of this star. And then towards the center, we have a tiny little white dot, and that is actually the central white dwarf, which is really cool that we can actually see that. And so real quick, I'm going to answer a few questions. So we have Daniel Millet's asking, why is the Triangulum Galaxy called so? And so the reason why it's called the Triangulum Galaxy, it's not really too complicated. It's in the constellation Triangulum. So it's there. So they decided to call it the Triangulum Galaxy, which is pretty funny. The Globular Cluster we just looked at, M15, it's called the Great Pegasus Cluster. It's because it's in the constellation Pegasus. So, you know, it's not really too creative sometimes with the naming of these objects. We have a request actually after this for M34. So M34 is an open cluster in Perseus. Yeah, we can see that. And then afterwards, we have another request for another open cluster. So we'll bounce back to these. So yeah, let's do M34. Thank you for your request, by the way. All right, so while we wait for this picture to load, let's talk a little bit about M34. So this one is in the constellation Perseus. So Perseus is currently kind of a little bit higher in the sky right now. This object, M34, is around 1,533 light years away. So it's actually fairly closer to us And the radius of this object is around 7 light years. So, not too big compared to the other objects that we were looking at earlier tonight. It's a really nice open cluster. And so something I forgot to mention earlier about these open clusters is that we actually have a lot of them in the sky right now. The fall/winter sky is just abundant with open clusters. So we have the Pleiades, we have some other objects coming up like the Beehive cluster, we have all these other open clusters in Cassiopeia. And actually, a lot of people don't know this, but the constellation Taurus and the Little Dipper are actually open clusters. So yeah, quite a lot of open clusters in the sky tonight. And so someone else is actually asking to see another open cluster. So we can try M11 or NGC 253 from Tom Sarko. So yeah, let's see. Oh, wild duck. Okay, totally. I don't know how good M11 is actually going to look because M11 is setting. It is part of what I call like the summer sky. So that is currently leaving us right now. So it might be a little bit too low, might, be a little fuzzy, but oh, actually it looks great. So here is the wild duck cluster. So the reason why this cluster is called the wild duck cluster is because there is this V-shaped formation in the cluster. Use your imagination to kind of find it. But apparently the V-shaped formation in this open cluster reminded someone of wild ducks flocking. So that is why they're called the wild duck cluster. A lot of these things, it's not super creative. So yeah, there's that one. And so something else with this object, so we have common names for different objects. So we have, like the wild duck cluster, or we have like the Whirlpool Galaxy or the Dumbbell Nebula. But those are just the common names of objects. There's actually more scientific names for these objects, and they have a catalog that they belong to. So a lot of these objects belong to multiple different catalogs. Some are called NGC catalogs or a Messier catalog, the M thing. So for example, this object is called M11 or Messier 11 or NGC 253. And so the M or the Messier catalog belongs to someone called Charles Messier. Charles Messier was a comet hunter, and he was trying to look for comets, and he was scanning the sky looking for all these different comets. And every time he would find something kind of fuzzy, and it didn't necessarily, he knew it wasn't a comet, but anytime he would just kind of scan the sky and find a weird object, he would write it down and be like, all right, not a comet. So this is number one. And so that's how kind of the Messier catalog got made. So that was quite a while ago. It was around like the 1700s or something like that. And so there's a total of 110 Messier objects in the sky. I don't really know the reason why he stopped at 110. I don't know if he just didn't find any more or if he just got bored. So I really don't know the reasoning why there's 110. But the NGC catalog, that catalog is way, way bigger. So NGC stands for the New General Catalog. It was started in 1888, but it's currently still kind of going. It has around like 8,000 objects, and it has quite a lot. I don't know necessarily how they decided to put objects in there, because there's all these different objects in the NGC catalog, as well as the Messier catalog. There's galaxies, clusters, nebulas. So yeah, those are the two main catalogs that we use at Lowell, just because they're pretty user-friendly and pretty universal. There's all these other types of catalogs that are used, quite a lot. But those are the two main universal user-friendly catalogs that we decide to use at Lowell. All right, so we have another request. So I think I was actually saying M11 is NGC 253. That's actually the Sculptor Galaxy. So apologies for that. But we can look at the Sculptor Galaxy, which is great. So let's look at NGC 253. And so this one is another kind of spiral galaxy. This one's a little bit lower in the sky, and I did just get a little bit of a warning that we do have some clouds moving in. So we'll look at the Sculptor Galaxy, see how good it looks, and then, yeah, see what else we can see from there, just because these clouds are kind of rolling in right now. And so we kind of have a picture coming in of the Sculptor Galaxy. So compared to NGC 891, where this one, it was completely edge on, and then Triangulum was completely face on, this one's like kind of tilted towards us, which is really cool because we can see a lot of the color and the spiral arms, but we can also see the structure of the disk, and we can see the detail in the central bulge of this galaxy. So I really like the Sculptor Galaxy. I think it's very pretty. And it's also part of our local group. Oh my God, that picture looks amazing. So again, in the arms of the galaxy, you can see that active star forming region, and then the very, very bright central bulge. And so a little bit of facts about Sculptor Galaxy. So it is 11.42 million light years away. So again, pretty far, but it's in our local group. Again, it's one of the closer ones to us. The radius is 45,000 light years across. Well, radius, not diameter. So again, it's a little bit bigger than Triangulum, a little bit smaller than NGC 891. And again, someone asked earlier, why is Triangulum called the Triangulum Galaxy? It's because of the constellation it's in. The Sculptor Galaxy is called the Sculptor Galaxy because it's in the constellation Sculptor. So great. All right, so let's see. We have another request from Jim Knoll asking if we can see both of the clusters and the double cluster in the same field. So why don't we go to one of the clusters in the double cluster? We actually, unfortunately, cannot see both of the clusters in the same field of view. They are just too spread out, so we can only get one or the other in the field of view. So let's look at one right now. Again, yeah, they're really separated out. So they're two open clusters that just so happen to be next to each other. Probably has to do with the nebula that they were formed in. Probably had two denser lobes right next to one another. And then we got these really pretty open clusters. And so this object, again, is really user-friendly to look through binoculars or a telescope that you may have at home. It's in the constellation Perseus, and you can actually see this one with your naked eye. It looks like a little fuzzball in the sky, so very, very user-friendly, very easy to find this object on your own. I highly recommend you doing it because it's super crazy. All right, so we have some other questions. So let's see. Does the orbital motion in globular clusters hint at excess dark matter, similar to the effect found in spiral galaxy orbital motion? So that question was asked by Eugene Stempel, and unfortunately, I don't really necessarily know the answer to that question. There is a lot of research that's still going on actively about globular clusters and especially dark matter. And I, unfortunately, am not a dark matter or globular cluster master. I don't know. I'm not too well versed in those. My research and a lot of my education is in planetary sciences. But that is a very, very interesting question. And I definitely will research that and hopefully leave a response in the comments to that. So I'm sorry, I cannot answer that, unfortunately. And then a question from Ed Zigo asking, are any of these galaxies in a blue shift? So I believe Triangulum is blue shifted. Yeah, so Triangulum is blue shifted. Someone was saying it's going to be a bystander in the Milk-Andromeda collision. So if you don't know what the Milk-Andromeda collision is the Andromeda Galaxy and the Milky Way Galaxy are going to collide one day. We actually know that the Andromeda Galaxy is coming. And so we kind of have these different shifts in the colors of these objects. And so we get a blue shift and a red shift. And so we get this red shift when objects are moving away from us. So it's the longer wavelength. And we get blue shifted objects when they're coming towards us. And so the Andromeda Galaxy is one of these blue shifted objects. Again, I think Triangulum as well. So this is our closest neighboring galaxy, the Andromeda Galaxy. It's really, really close to us. I believe it's like 2 billion light years away or something like that. So it's fairly, fairly close. And again, we know this collision is going to happen just because it's actually already happening. So I was speaking earlier about the halos that galaxies have, and the Andromeda halo and the Milky Way halo already are interacting with one another. And there was recently a paper talking about that. So we already see this interaction happening. And so, but don't fret, this collision won't happen for a very, very, very long time. So relative to our time scales, galaxies are pretty static. They're, not really moving to us at least, but in the general retrospect of space-time, they're also moving and having their own collision interaction events. So we don't really have to worry about that anytime soon. All right, so we have a request for the butterfly cluster. So unfortunately, the butterfly cluster is in the constellation Sagittarius, which has already set in Flagstaff. So maybe a little bit in the summer next year we can get the butterfly cluster again, or actually maybe a little bit as soon as the sun sets you can get the butterfly cluster. I just don't think we'll be able to get it through the plane wave, unfortunately. But so it is getting a little bit close to time, so we're going to move on to the planets. So we have a lot of planets up in the sky right now, some that are really close to being set. So let's look at like Jupiter before it gets too low. So the order I'm kind of going to go into is I'm going to look at Jupiter, Saturn, see if we can see Neptune, I don't know, Mars, and then Uranus. That's kind of the order that these planets are in the sky right now. We actually also have Pluto up in the sky tonight, but Pluto is just so dim and it looks so much like a star that if we look at Pluto through our telescope, you really can't figure out which one it is. It just looks like the background of stars. So to see Pluto, you actually have to take pictures of it on consecutive nights, and then you can actually see Pluto moving in its orbit, and then you can be like, oh, okay, this one's Pluto. So that one's a little bit harder to see through our telescope, but we have a really beautiful view of Jupiter up right now. And so right now we have the exposure turned up so we can see the moons of Jupiter. So we have the 4 Galilean moons. And then when we bring the exposure down, you can actually see the atmosphere on Jupiter. You can see some of the stripes on the planet. And so again, Jupiter is a gas planet, so it doesn't have a surface necessarily. We don't even know if it has a core. And the atmosphere of Jupiter is made up of all these different layers of gas. Some are heavier than others and some are lighter than others. And so the reason why we get these really cool stripes, and if you've ever seen pictures of Jupiter, we get these really cool swirling colors, kind of looks like marble watercolor effects. That all has to do with the differentiation of the gases in the atmosphere of Jupiter. And so again, because they're different weights and Jupiter's spinning super, super fast, all these gases are kind of being swirled around at different rates. And so we get these really cool patterns on Jupiter's surface, or not surface, its atmosphere. So I think Jupiter is really pretty. And then again, the moons, the Galilean moons are also very pretty. So we have 4 of them. So we have Io, Europa, Callisto, and Ganymede. And so there is a lot of interest when it comes to Jupiter's moons because a lot of them are made of icy/rocky material. And so for the search for extraterrestrial life and astrobiology implications, they're very desirable right now. Something that's really cool about one of the moons, Io, is that it's the most geologically active body in the entire solar system. So it has so many volcanoes on the surface. I think there's around like 30 active volcanoes erupting on the surface, completely resurfacing the moon. So Jupiter has some really, really cool moons. But not only does Jupiter have cool moons, Saturn has some really awesome moons as well. So let's go check out Saturn. And planned to go to one of Saturn's moons coming up here. So it's the Dragonfly mission. And the Dragonfly mission will be landing on Titan, which is a moon that it's rocky and has some ice, we believe. But the really interesting part about Titan is that it has an atmosphere of nitrogen and then lakes on the surface. So actual liquid lakes of methane and ethane. So it's not water, but it's the only other body in the solar system that we have actually observed this stable liquid in large amounts. So it's really enticing. We're like, oh my gosh, it looks like Earth, but it's like super toxic. It's nitrogen and ethane and methane. So we've already sent a mission there. So that was when Cassini went around Saturn to take a bunch of pictures. Cassini had a lander on it called Huygens, and they actually shot Huygens off onto Titan. And all it did was just plop on its surface, take a few pictures, take some data, and then it stopped working. So Dragonfly is supposed to actually be like this big rover copter thing, and it's going to fly around, hop around, take a bunch of pictures, take some data of the atmosphere. I believe it's supposed to look at the liquid lakes as well. Tell us more about Titan and the processes that are happening, because they're super alien to us on Earth. You know, we don't really see anything like that happen here on Earth. So it's really cool and really exciting mission. And then again, so we have this exposure turned all the way up so we can see the moons. And so when we turn it down, we can actually see the rings and we can see the planet itself. And so again, Saturn is another gas giant, and we have some really beautiful rings around that gas giant. And so Saturn's not the lone planet with rings. Jupiter, Uranus, and Neptune also have rings, but we can't see them just because they're so diffuse and they're so spread out. And Saturn's are very, very close together and more thick. And so that's why we can see them very well. And so we actually don't think the rings, were there for super long. We think they actually formed recently around, dinosaur age, and then they're not going to last too long as well. They're probably going to coalesce into moons and get ripped apart and everything. So the rings won't last too long either. But while we're on the topic of rings, let's go to Uranus. So like I was saying, Saturn's not the lone planet when it comes to rings. Uranus, Neptune, Jupiter have rings as well. And the rings of Uranus were actually in partly discovered here at Lowell Observatory. So we have an astronomer, Larry Wasserman, and he was on the team that helped discover the rings of Uranus. And so again, you can't really see them visibly. You need, like different filters and wavelengths of light to really see them in all of its glory. But what's really interesting about the rings of Uranus is that they're actually going straight up and down. So when you think of Saturn, you think of, it's a planet and the rings are kind of horizontal. But the rings of Uranus are flipped up and down because the axial tilt of Uranus is completely on its side. So we actually think Uranus got knocked over during its formation. Something probably hit it really hard. We don't necessarily know exactly, that's just our theory, but something hit it really hard, knocked it on its side, and so the rings are going up and down, which is pretty cool. And so, yeah, another gas giant there, but this is more of an icy gas giant just because it's so far away. It's around like 2 to 3 billion miles away, so it gets really cold. All right, and last but not least, let's try Mars. And so Mars is my favorite planet. I am pretty biased because a lot of the research that I do is on Mars. And I think Mars is just super, super cool. It's our little red planet. It's a lot smaller than the Earth. It's actually really tiny compared to the Earth. And Mars is really red because we have iron oxide on the surface. So we have a lot of kind of rusty material, and that's not the only reason why. It has a lot of sandstone. So think of like Sedona or the Grand Canyon. The reason why it's really red is because of the rocks. And so Mars at one point had a lot of water on it. And so that water helps create some of these really red iron oxide kind of rich rocks on the surface. And what's really cool is, surprisingly, we have a really good view of Mars tonight. And so if you pay very, very close attention, kind of to the top, in between the top and the left of Mars, you can see a polar cap. And so I believe that is the south polar cap on Mars. The south polar cap is a lot tinier than the north polar cap. And we can see some of the dark spots on the surface. So it's kind of like the mare on the moon. So it's a lot of basalt or volcanic rock that's on the surface of Mars. Mars had a lot of volcanic activity as well. And then the polar caps are mainly made of CO2 and water ice. And so during the summer, which I believe it's summer right now on Mars, Mars has a lot longer seasons than we do here on Earth. But the polar caps on Mars, during the summer, all that water or all the CO2 ice kind of sublimates away. And so we're left with a lot of water ice in the caps. And then when it turns winter again, that CO2 kind of condenses again, and it makes the polar caps a lot bigger. So it's really cool to see this variation in the polar caps. And yeah, again, Mars is my favorite planet. Okay, so I believe that is all that we have for tonight. Thank you guys so much for coming. I appreciated all the requests and all the questions. Again, if you have any other questions after the live stream that you so happen to think of, please leave them in the comments. We'll definitely get to them. And be sure to check out some of the other live stream events that we have coming up every Tuesday. We have interactive stargazing. So if we didn't get to an object that you would like to see tonight, you have next week and the week after that. Of course, it's all dependent on the weather. And it is getting a little bit chillier up in Flagstaff at night as well. And don't forget, we also have the premium access still going on at Lowell. We have our Dyer telescope, and the Godo, I believe, is still having premium access events, reservations going on. So definitely check those out. The Dyer telescope and the Godo telescopes are super, super cool. I love working them. I think they're my favorite. And so we actually have the Clark too. So we have the Clark until the end of November. So definitely check those out because the Clark one is going to be ending soon. But again, thank you guys so much for coming tonight. I hope you guys have a very stress-free night. And yeah, thank you so much.